Is it started?
Yeah.
Thank you. Okay. We're going to learn about Doppler effect today. And I'm going to teach you how it happens. We're going to see some examples of it. And we'll see some ways that we use the Doppler effect to benefit us. So first, Doppler effect. Someone describe the Doppler effect to me. What is the Doppler effect? What's that?
Like an increase in frequency is increase in pitch or height.
Okay, great. Thank you. Pooja says an increase in pitch, an increase in frequency. Under what circumstances? Yes, Sean.
Isn't it visible or apparent change in frequency?
Good. Under what circumstances? When does this happen?
In water?
Okay. Cheyenne?
Isn't it in motion?
What's in, is this in width? What's,
Like in motion?
okay, what's got to be in motion?
The source of the sound.
Okay, you guys okay with that? When the source of the sound is in motion, then you get a change in frequency or pitch. Tell me, when the source of the sound is approaching you, what happens to the pitch? Does it get higher pitch or lower pitch?
Higher.
Good, higher pitch, right? And when the thing is fleeing you, what happens to the pitch? Higher or lower? Yeah, the pitch that the source is putting out hasn't changed. It's just the frequency that you perceive has changed, right? And that's Doppler effect. The most common mistake people make is they'll use terms like loudness or amplitude. And Doppler effect has nothing to do with loudness or amplitude. It's not the amplitude that's changing, it's the frequency. And it's the perceived frequency that's changing, you know? Or really the frequency that, that the person perceives. So here we go, Doppler effect. Change in perceived frequency of a wave when source moves, well, I'm giving a longer, towards or away from observer. Change in perceived frequency of a wave when the source moves towards or away from the observer. That's your Doppler effect. But I just said it's when the source moves or away from the observer. For example, you know, in a car race, has anyone ever gone to like a auto car race or drag race or NASCAR thing or whatever? Okay, and so you've experienced when the car is moving really fast, as it's coming towards you, it's and then as it goes away from you, you know, that classic sound. Okay, that's because the source of the sound is moving towards you or away from you. But does this also work if the observer is moving towards or away from the source? Do you still get Doppler effect when the observer moves towards or away from the source? Yeah, absolutely. Sure. Okay. The biggest example you get that is in movies when you have people on a train and the train is approaching a crossing guard, right? And the crossing guard is going ding, 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 ding. But when the train goes, the train's going ding, 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 ding. Have you ever heard that sort of sound? The classic stock people on a train sound? Yeah, so I just want to let you know it's not just a change in perceived frequency of a wave when a source moves towards or away from the observer, but it also happens when the observer moves towards or away from the source. It goes both ways. Let's see why that happens. So I want you to see Here the source is stationary, and he's putting out a wave, a disturbance in all directions, maybe like a pebble dropping into a pond. And so you see, you get these concentric circles that come out, like the waves where the pebble dropped in a pond. And there's no Doppler effect. But look what happens when the source is putting out waves and moving also. This source is moving to the right. What do you notice happens to the waves here if you are in front of the source? Raise hands so I know to call them. What's happening to the waves? Yes?
Smaller.
Smaller
like
what?
Wavelength.
Yeah, good for you, Pooja. You guys okay? Smaller wavelength. These waves have a smaller wavelength. Okay? Now, is the speed, once this guy gives off the wave, is the speed of these waves any different than the speed of these waves? No way. We talked about that the other day. So wave speed is the same for all waves, regardless of frequency or wavelength. Okay? So if we look at this formula, V equals F lambda, I'm telling you that those waves, whether you're in front of the source or behind the source, those waves are moving at the same speed, the speed V. But because the wavelength is smaller, what's going to happen to the frequency? Yeah, it's going to go up. Frequency goes up. Smaller wavelength, bigger frequency. Because they have to multiply to make the same number, the speed of the wave, which doesn't change. What's happening to the waves here? If you're behind the source, if the source is fleeing you, what's happening to the waves here? Say again?
They'll get
What gets smaller?
smaller. Wavelength.
Not here. Compare these wavelengths with these wavelengths.
I thought you said what's going on.
What? Oh, you think I was like, I was here? Okay. Yeah, if the source is fleeing the observer, the wavelengths, that is the distance between successive crests, and we're kind of assuming each black line is a crest, the distance between successive crests is going to be bigger. Bigger wavelength, lower frequency. Can someone explain in their own words, why are these wavelengths getting smaller? I mean, I see it, I believe my eyes, but could you explain why these guys are getting smaller? Like, what's going on here? Yes, Maxwell? Okay, true. But I'm asking, like, why are the wavelengths getting smaller? Not because as a result of them getting smaller, you're right, higher frequency. But why are they getting smaller in the first place? Yeah, Anise.
Like, I want to say because they can only go so far until, like, it's gotta stop.
Okay, can only go so far. Tell me more. Why are these wavelengths smaller? Yeah, Pooja?
Because the source is moving to the right. Or, yeah.
Okay, so the source is moving to the right. So the source puts out a wave. The wave travels to the right a little bit. But, go ahead.
The distance between the source and the observer is closing in, so it's like they're screeching.
Okay, but you know that whether an observer is there or not, it doesn't affect really the wavelength. I mean, let me just tell you that. Okay, here's the source. Alrighty, and let's say the source puts out a wave. Alrighty, he releases a wave. Then a moment later, that wave is going to be here, and then he releases another wave. And a moment later, that wave is going to be, this wave will be there, and that wave will be there. You see what I mean? But what if this guy's in motion? He releases a wave. A moment later, this wave is here. But this guy's moved. He's here now. So he releases a wave. And do you see how these two successive waves are closer together? Now, this wave moves to here. This wave moves to here. And it's time for this guy to release another wave. But the thing is, he's moved. So he releases another wave. And again, these waves are getting closer to each other because the source is catching up to the waves. Does that make sense? Okay, I'm going to show you an actual demonstration of this. It's a lame demonstration, but it's a demonstration nonetheless. I'm going to need to make sure that we don't trip over this thing here. Okay. Does someone feel comfortable catching pieces of paper thrown at them? Come on up. Thank you, Paul. You're okay? Stand there. Take a couple steps back. Okay, great. Now, I'm going to throw pieces of paper to Paul at a particular cadence, and that's going to be the frequency with which he has to catch the papers. Are you guys ready? Here we go. Oh, oops, that's okay, dude.
I'm in band.
That was a bad throw. But he was doing okay. It was pretty easy, except, he wasn't catching them. But now, I'm going to do, here I got it. I'm going to do something else. I'm going to throw papers to him at the same cadence while running towards him as fast as I can. Okay? So what's going to happen is I'm going to throw the first paper to him, and by the time he's catching it, I'm not here anymore. I'm over there. And I'm throwing him the next paper, and by the time he's catching it, I'm not over there. I'm right next to him. And then I throw the paper. You see what I mean? And so the paper is going to hit him with a higher frequency, and it's going to be harder for him to catch. You ready? Here we go. You in the face. Well, I have to tell you. Thanks, Paul. Give Paul a big hand. This is not a very good demo. It doesn't really demonstrate it, except it does. I mean, I want you to see that it matters if the source is moving towards you. They are going to come at you at a higher frequency. Whether or not I actually demonstrated that, who knows? Okay. All right, one more thing I want to talk about. What happens when the source is moving at the same speed as the speed of the wave? What do you notice? What do you notice is happening here? The source puts out a wave, then he catches up and puts out another wave and stays with that wave and puts out another wave. What's happening with all the waves here?
They're all,
What's that?
they're all like at the same.
Yeah, all the waves are at the same place. They're all piling up, correct? Which means if you can think of sound as compression and decompression waves, what's going to happen to that pressure here in front of this plane as all these waves pile up? What's that?
It's going to get really big.
It's going to get really big, absolutely. And that doesn't happen just when you go the speed of sound. It also happens when you go faster than the speed of sound. Do you notice this guy? He's going faster than the speed of sound. And so you get this cone here. There's a name for that cone. It's called a Mach cone. You get this Mach cone where all of the sound waves are piling up along this line here. So if you're an observer and you happen to be standing there, and then this Mach cone goes over you, what do you hear? Say again? Yeah, boom. What do we call that boom? Yeah, sonic boom. You hear a sonic boom. And that happens when a plane is traveling at or faster than the speed of sound. You get to hear a sonic boom. How many people here have actually heard a sonic boom in their lives? Okay, where were you? Sion, where were you?
I watched it on YouTube.
Okay. Has anyone ever actually experienced it in real life? Yeah, Gavin, where were you?
I was at an air show.
Okay, air show. How about you, Paul? Where were you?
I was at the air show.
Air show. Was any good? That's where you'll hear them, definitely. Was anyone here at like the landing of a space shuttle? Back then? Because that was the most common place to get sonic booms. But yeah, air shows. Beautiful. Are sonic booms loud?
Yeah.
Extremely loud. Now, could you imagine being a 5-year-old boy, which I was in the mid-'60s, okay? And I probably heard a sonic boom every couple weeks. So every 2 weeks, I would hear this incredibly loud sound, you know? It would rattle the windows, make babies cry, scare me. I was actually afraid that the plane was going to fall on me, so it really, truly scared me. And I had to put up with that every 2 weeks. But you know why we don't have sonic booms anymore? Government. Government. They stepped in and said, you know what, guys? You don't get to travel faster than the speed of sound over populated areas because sonic booms are really scary. They make dogs bark. They activate car alarms. They make babies cry. No, you know, guys don't get to do it. And they say, no, but we'll lose money. And government said, no, we're going to regulate you. Thank God for government. And thank God for regulation. Because now you guys don't have to put up with sonic booms all the time. Right? So I just want you to think about that when you say your prayers tonight. Thank God. Thank you for government. Thank you for regulations. Okay. It is now time to learn an equation for a Doppler effect. Oh, hey, I didn't do my demo. Oh my gosh. Hey, you guys. I forgot to do this. I need you to actually experience Doppler effect. Oh. Wait. I give up. This thing's broken. Here, I tried to fix this like during SSR. Let me see if this works. Okay. You guys hear that? And that's a constant frequency, right? Or combination of frequencies. Okay? So I want you to hear how it changes. Are you hearing that change? You're afraid it's going to come loose and kill you? That would suck if it hit one of you guys like in the face and it hurt you. Then I'd lose my job. But are you hearing that okay? Are you hearing variations in frequency? I wonder if it'll come up in the video. And are you able to detect this higher frequency as it comes towards you and lower frequency as it goes away from you? I gotta point it towards you guys.
We all
Couldn't have this, and it didn't hit anyone. Cool. Alrighty, well, it works. I'm happy. All right, now it's time for you to learn a formula for Doppler effect. Okay, if F equals the frequency of the source, F prime equals the frequency perceived by the observer, then here's the formula that relates them. The frequency perceived by the observer equals the frequency of the source multiplied by V plus or minus V sub O over V minus plus V sub S. You do not have to memorize this formula. It's not on the AP exam. When I give it to you on an exam, I will give you the formula. It turns out V is the speed of the wave in whatever medium you're in. V sub O is the speed of the observer. Oops. And V sub S is the speed of the source. By the way, I want to tell the television audience that there's actually a cool derivation of this, but I don't spend my time on it anymore. But it's kind of interesting to see where it comes from. It's pretty simple, but time consuming. Okay, and then do you notice that this says plus or minus, but that says minus plus? My position of those signs is important. There's a top position and a bottom position. Top position and bottom position, okay? You're going to use that upper sign the upper position for approaching. That is, if the observer is approaching the source, you use the upper sign. If the source is approaching the observer, you use the upper sign. The lower sign is going to be for fleeing. If the observer is fleeing the source, you use the minus. If the source is fleeing of the observer, you use the plus. When I was on my honeymoon with my wife, with my first wife, who's my only wife, she's still my wife. See, and this is the day of Trump, right? Did you guys, how many people watched the thing last night? Okay. There's several things, several images I have. Did anyone really notice how freaky weird Melania looked?
Yeah.
She looked like a frozen statue.
She's a lizard lady.
What did you think? She looked like a lizard lady. She didn't stick out her tongue, did she? But yeah, okay, so yeah, I mean, that was just freaky. She's like a frozen statue lady. She was freaky weird. And so different from Michelle, right? I mean, as different can be. It's just freaky. Okay, well, I don't want to get too controversial, too political, because this is going out on YouTube. But yeah, it's a really freaky. Okay, I got to tell you one more thing. State of the Union. Okay, and maybe I'll be off camera as I say this, so one good. So. Oh, do I need to move more? Okay, great. I gotta tell you, was it just me? Remember when he was lauding that African American unemployment was the lowest it's ever been? Did that feel weird to you?
Yeah.
Okay, why? Why did it feel weird? Because I've got my reason, but I just want to hear what you guys think.
Well, wasn't he trying to appeal to the opposite party by mentioning that?
Yes. Yeah. He's yeah. Okay, and I'm just going to tell you my reason. Here's a dude, right, who spent his first several years, being in politics, claiming that the first black president wasn't a citizen and was not, was illegitimate, right? He's the guy who says that white supremacists and Nazis are very fine people, right? He's the guy who's restarting the war on drugs so that, white people and black people, they take drugs at the same rate, but black people are 3 times more likely to be arrested for drugs than white people, even though they do drugs the same rate. So he's restarting that war on drugs. And of course the NFL thing, why did he say NFL players? Well, I mean, because they're black. That's why he hates that they kneel during that. Okay. And then this dude is saying, okay, black unemployment is low. He reminded me of the abusive husband who beats up the wife and then drags her with her tear-stained face to a nice restaurant and say, baby, you never had it this good. So it's just freaky weird. It felt really creepy to me, spent all this time beating his wife and then coming to me. You never had it actually. Okay, well anyway, now I'm back on camera. Okay. So I'm on my honeymoon with my beautiful wife, and we go on a high-speed train. And has anyone ever been in Europe and gone on a high-speed train? Have you? Where were you? What country were you in?
The London, Paris.
Okay, so you were on the Channel. Yeah, Channel, right? Yeah. I gotta tell you, high-speed trains go incredibly fast. You have no idea. Yes, sure. If you gotta go, you gotta go. Yeah. So yeah, they go 400 kilometers an hour. They go 240 miles an hour, right? Faster than you could ever imagine. You look out the window and they go really fast. Okay, you guys okay with that? Okay, so I got 2 trains, and this happened to me and my wife many times. We did it in Spain. No, in France. We were in France when we took the high-speed train. We went from Paris to the south of France on a high-speed train. Okay, so we got 2 trains approaching each other. At approximately 220 miles an hour, 100 meters per second. They're approaching each other at 100 meters per second. Speed of sound in air is 340 meters per second. And the source is a train whistle at 200 hertz. The source frequency is 200 hertz. These two trains are approaching each other. What frequency do I hear? What frequency does the observer hear? Well, I'm going to do this problem. You got frequency equals the perceived frequency equals the actual frequency. The train whistle is about 200 hertz. The speed of sound in air is 340 meters per second. Because they're approaching each other, I'm going to have to use the positive sign in the numerator because the observer's approaching the source. I'm going to have to use the negative sign in the denominator because the source is approaching the observer. And when I multiply that out, I get 367 hertz. That's the frequency I hear when these trains are approaching each other. And that frequency doesn't change. Whether the train's 100 yards away or 50 yards away or right on top of me, it's going to be 367 hertz. It'll get louder as it comes closer, but that frequency stays constant. Something like that. Okay, great. A moment later, the trains pass each other, which means now they're fleeing each other. A moment later, they flee each other. I'd like you now to find what's the perceived frequency. What frequency am I hearing as the observer now that these two trains are fleeing each other rather than approaching each other? Please do that now. Well, if you don't know what you're doing, this is what you're doing. I hope you notice that the signs are going to change in the numerator and the denominator because they're now both fleeing each other. What frequency did you guys got? 109? 109 hertz. 109 hertz. Tell me, if I double the frequency, do you know what, those of you good at music, do you know what interval that is when you double the frequency of a tone? Like, is it a third or a fifth? Or... Yeah, good for you. It's an octave. It's an octave. So if this tone I'm hearing as they flee each other is 109, an octave higher than that is 218, and an octave higher than that would be 436. So do you see that the tone as they approach each other is almost 2 octaves higher than the tone as they flee each other? I have to say that's by far the most extreme Doppler effect I'd ever experienced in my life. You know, I mean, to hear, you know, you're used to, you're not used to, oh, you know, I mean, I can't get that look because my voice is kind of thrashed right now, but yeah, I mean, you're not used to that level of Doppler effect. And so I actually explained this to my wife. I taught her about Doppler effect and told her why it was so noteworthy, and I think she fell in love with me all over again. It was beautiful, yeah. Yeah, she said, wow. Now, the final thing is I want to talk about like essentially 3 applications of the Doppler effect: motion detection, Doppler radar, and then the blue shift and red shift. And we'll have to see. I'm not going to get to blue shift, red shift. I may not even get to Doppler radar, but let's go for it. Applications of the Doppler effect. And the first one is motion detection. Okay, so here's the door to a supermarket, and here's your little motion detector, alrighty, and here's me walking towards the door. Someone explain to me, how does this thing detect my motion? What happens?
It can emit like.
What's that?
It can emit like little frequencies.
It's gonna emit waves? That's what you're thinking? Okay, this guy's gonna emit waves. Hey, that's great. So here's the waves it's emitting. And then what? What's that? Okay, they're gonna bounce back. And if I'm in motion, what are they gonna look like when they bounce back? Thank you. Good for you, Izina. You guys okay with that? When these waves hit me, they're going to have a particular wavelength. But if I'm walking towards the motion detector, they're going to hit me and come back at a lower wavelength. Because I'm walking towards the detector. I'm like the source who's walking towards the observer. So they're going to reflect off of me and come back at a lower wavelength. This detector is going to calculate, notice, it's going to compare the new wavelength with the wavelength of the output waves and go, oh, there must be motion. So tell me, let's say a car is parked here and the car is just standing still. Why is this door not going to open? If the waves are bouncing back, why won't the door open if the car is just sitting there parked? Yes?
Because it bounces back with the same wavelength.
Good, it bounces back with the same wavelength. That way they don't have to worry about these stupid doors always opening if there happens to be a bicycle or a car or a shopping cart right there. You know what I mean? They want to make sure they only open when there's motion. Yeah. Great. Let me ask you another question. What if I sent a wave out and just timed how long it took for the wave to come back to me? What am I doing? Am I detecting motion? What am I detecting if I send out a wave and time how long it takes for it to bounce off of something and come back? What am I measuring there?
The frequency.
What's that?
The frequency.
No. What's up, Pooja? Yes, you said distance, didn't you, Pooja? Come on. Yeah. Yeah, you guys okay with that? You're measuring distance, right? What animal does that? What animal puts out waves and measures how? Yeah, bats, echolocution. That's what bats do. But this isn't what a bat does. This he doesn't care where I am. He only cares that I'm in motion. Okay, so that's how motion detectors work. Now, I want to share with you, when I was a little kid, this is not what was used to open supermarket doors. What they used was you had a rubber pad, and under the pad was a pressure-sensitive device, and you stepped on the pad, and the act of stepping on the pad would open the door. So sometimes those pads, I was 5 years old, I was very light, and sometimes I would step on the pad and I couldn't open the door. I'd have to jump up and down on it in order to open the door, But then these guys started coming out, and of course, being a scientist, I wanted to investigate them. So I thought, okay, how sensitive is this device? How fast do I have to move in order to activate the device? So I started doing this. I'd see a device there, and I'd stand like this, and then I would just do this, right? And pretty soon, I could get up to the door because I was not moving fast enough to have the change in the wavelength be significant enough. And so then I'd be up against the door, and now I'm in front of the glass door, and so I just go, and then the guy would walk towards it, and then they'd activate it and open it, and I'd go, oh, thanks. All right, well, hey, that's it. Tomorrow we talk about Doppler radar, red and blue shift, and other stuff. So thanks a lot. Bye-bye.
This is